Good morning, everyone. Very quickly, we're going to try to speed run the second exam from spring of 2021. So this is last year's exam. We're looking at it right now. Looks like a normal exam, all of the usual sorts of things, instructions, academic security, integrity, authorized resources. Read those on your own time. Immediately, we get to the formula sheet. So formulas here are mostly things that we would be expecting. We've got all of the same things that were on GR1. Notice the coefficient for beta 1 hat, right? OLS estimate. We've got beta 0 hat, the OLS estimate. We've got a formula for a t-stat, confidence interval, the omitted variables bias formula, so the expected value of beta 1 in a model that you leave x2 out of when x2 should have been in the model. Well, beta 1 is going to be biased. The standard error of beta 1 hat in a model with two variables, x1 and x2. Notice that all of the usual parts are here. The amount of variation in the residuals from the model, the amount of variation in the right-hand side variable x, the size of the sample you used, and then something to do with the correlation between x1 and x2, where more correlation is going to cause inflated variance. And then down here at the bottom, this is the only new one. Okay, so we've got the formula for an F statistic here. You'll remember how this thing works. You've got something to do with two different models. One model where you impose a restriction that you get to choose, and one model where you don't. And the sum of squared residuals in the restricted model, if the restriction is really meaningful, meaning that it causes the model to fit the data much, much worse, the sum of squared residuals is going to be a lot larger in the restricted model than it is in the unrestricted model. And so this is going to be a positive thing, something up here to do with degrees of freedom. The difference between these is the number of restrictions, and in the denominator, again, the sum of squared residuals from the unrestricted model and the degrees of freedom from that model. So all of this formula is just to compare the goodness of fit between the restricted model and the unrestricted model, but the rest of the formula maps this into something that actually conforms to the F distribution so we can look up critical values for it. Here we go. Problem 1. Suppose an economist is interested in determining the relationship between education and labor supply. He estimates the following model for a sample of employed people. So we've got hours worked, usual hours worked per week, as a function of education. I'm guessing this is years. Yep, just as it usually is. Education in years. Education squared. Okay. Rich and poor. What are these? Rich is a dummy variable equal to 1 if a person's income is over 100,000 per year. Poor is a dummy variable equal to 1 if a person's income is below 20,000 a year. Notice that there's a big gap in the middle between 20,000 and 100,000. Lots of people are in that range. So there's also a variable called midinc equal to 1 if a person's income is between 20,000 and 100,000. Not included in the model. Yeah, I see that it's not included in the model. Of course, if it was included in the model, we'd have a dummy variable for each of the three groups, and there'd be a perfect collinearity problem. So we're going to leave one of them out. Reg, hours worked per week on education, education squared, rich, poor. Here it is, all the output. So in the big picture, we see that actually this model explains about 24% of the variation in the data, which is not bad. I don't know how much variation there is in usual hours worked. Looks like it has a standard deviation of about 11. So some people are working 11 hours more than average. Some people are working 11 hours less than average. Education, education squared, rich, poor. Yeah, rich people work more. Interesting. Poor people work less. You can debate which way you think the causality is going there. Write a one-sentence interpretation of beta 3 hat, the coefficient on rich, using the numerical value in your sentence. You get to do this using your own words. So the solutions say on average and controlling for other factors, rich people tend to work 4.8 hours per week more than middle income people. That's nice and precise. I would say in my own words, holding all else constant, I expect a rich person to work 4.8 hours more than others on average. Of course, I said expect and then I said average, so I kind of said that twice, but just to make sure we're clear on what expectations mean. Write a brief interpretation of beta 2 hat, the coefficient on education squared. Explain the intuition behind the observed relationship. Now, this one's a trap. Be careful here. You look at this and you say, okay, education squared going up. I see a coefficient of 0.01, so education squared goes up, and hours work also goes up, except I can't make the usual statement about this thing where I say holding all else constant, because of course education and education squared are very much the same thing. If education goes up, education squared goes up, and if education squared goes up, education goes up. There are no negative numbers in education, right? Strictly positive. Or potentially zero, although I suspect that that's a very rare outcome for people. So brief interpretation of beta 2 hat, the coefficient on education squared. For this, you can write it the usual way, but the best way to think about this is if education increases, the marginal effect of education, because education squared is in the model, the marginal effect of education is a function of education. And I see that this is positive, so I know that the marginal returns to education, or the marginal effect of education in this case, is increasing, right? As education goes up, notice you start off with a negative coefficient. For very, very low values of education, the marginal effect of education is going to be that people work less. And this says that that is going to start turning around. And maybe as education gets to high values, we see people working a little bit more again. So on the solutions, this one is actually crossed out, and we said it was a bad question. But the answers that you might write are the usual thing, where you might say, holding all else constant, if education squared increases by 1 unit, I see usual hours worked increase by 0.01 on average. The good, clear answer here would be to say, hey, this means that the marginal effect of education is increasing, right? Starts off negative, but it increases as education increases. That's what I like to think when I see a coefficient here. I look at the sign and say, the marginal effect is actually increasing. What would you expect to happen if mid-inc were added to the model? Well, I guess I already gave this one away. Would the poor and rich coefficient estimates decrease? No, not necessarily. Would the standard errors on the education and education squared coefficients increase? Not necessarily. One of the variables, poor, mid-inc, or rich, would be omitted from the model. Yeah. So we've got the constant here is the constant when rich is equal to 0 and poor is equal to 0. So if you're not rich and you're not poor, guess what? You're in the middle income range. And this constant is the constant for you. And this basically tells you if your education and education squared were 0, you're not rich or poor, I expect your hours worked per week to be 43.7. 43.8, call it. So that's mid-inc. If we add a dummy variable for mid-inc, that dummy variable would tell us the average difference between the middle income group and the baseline. The baseline in this model was the middle income group, so I don't want to know the difference between middle income and middle income, right? But I see that rich people are 4.8 hours a week more than the baseline group, which was middle income. Poor people are 12.5 hours per week less than the baseline group, which again was middle income. So R squared would increase dramatically? No, actually it wouldn't increase at all. In this case, if you added mid-income, you'd have to drop one of them to solve the model because all three are now included. And dropping one of them means you're going to be back to exactly the same spot that you are here in terms of model fitting power, right? So we would have a linearly equivalent model if you put rich and mid-income and left poor out. Then poor would be the baseline, but all of these numbers would adjust accordingly. R squared would be exactly the same, fitted values exactly the same, root mean squared error exactly the same. Feel free to try it. 5 points. A researcher wishes to test the null hypothesis beta 3 is equal to beta 4 against the alternative hypothesis that it isn't. Explain the meaning of the null hypothesis in layman's terms. Okay, beta 3 and beta 4 here are going to be the coefficient on rich and poor. So the meaning in layman's terms would be that rich people and poor people differ from the baseline, middle income people, by the same amount. And right off the bat, I'm very skeptical about this one because it seems like rich people work more than mid-income people, and it seems like poor people work less than mid-income people. So I would be very surprised if I could run a statistical test that these two numbers, 4.8 and 12.5, are actually the same. I think I would be maybe shocked if that turned out to be true. Explain the meaning of the null hypothesis in layman's terms. Well, like I just said, rich people and poor people differ from the baseline by the same amount. Notice that we're not requiring those coefficients to be zero. That would be a different null hypothesis. We're just saying that these two coefficients are equal to each other. I could add another restriction and say they're equal to each other and they're equal to zero. So they're both zero. But that's not what we're doing here. Derive a restricted model appropriate for the hypothesis from part C, simplifying as much as possible so that you could estimate this model in Stata if you had appropriate data. Here's what we do, right? I've got a null hypothesis. I need a restricted model. And as you can imagine, there's going to be something about an F-test, right, in the next step. So the F-test is going to compare a restricted model to an unrestricted model. I already have an unrestricted model where I estimated these coefficients and let them be whatever they want to be. Now I need to estimate a model where I force them to be something that I specify, which is my null hypothesis. Then I can compare how good that model is to how good this model was. And if the restricted model is really bad compared to this one, I'll reject the restriction. How would I do that? How would I create a model where beta 3 is equal to beta 4? Well, this is a little bit clever, right? But if I made one variable that was rich or poor, instead of having a variable for rich people and a variable for poor people, but one variable in the model for rich or poor people, then whatever the coefficient on that is, it can still be anything it wants. I'm not going to require it to be zero, but that coefficient is going to be the same for rich people and poor people. How would I do that? Well, rich is equal to 1 if you're rich. Poor is equal to 1 if you're poor. They're both equal to 0 all the rest of the time. So if I come up with a new variable that is equal to 1 if you're rich or poor, that's exactly what I want. And guess what? Rich plus poor, because rich is 1 if you're rich and 0 otherwise. Poor is 1 if you're poor and 0 otherwise. Rich plus poor would be 1 if you're rich or poor and 0 otherwise. So let's do that. Let's say ours. My restricted model will be something like this. Ours. Go away, keyboard. Is equal to, let's say, beta 0 plus beta 1 education plus beta 2 education squared plus beta 3 rich plus poor plus UI. Error term. I guess I should put eyes on education and hours also, right? Perfect. Simplifying as much as possible so that you could estimate this model in Stata if you had appropriate data. If I've got rich and poor, I can absolutely make rich plus poor in Stata. Generate a new variable equal to rich plus poor. So that's perfect right there. Now, compare this to the other model that had beta 3 rich and beta 4 poor. Basically, I'm just forcing this coefficient to be the coefficient for rich and poor. The partial output below shows the results of the correct restricted model from part D. Use this and the other information in the problem as needed to test the null hypothesis. Beta 3 is equal to beta 4 versus beta 3 is not equal to beta 4. Okay, so here's what we've got. I've got a restricted model. I've got an unrestricted model. Indicate which statistic you are using. TF p-value. Use an appropriate test of your choice and a 95% confidence level. I will warn you right now, don't try to use a t-test. Don't try to use a p-value from Stata, right? You could be very tempted to go and look at it and say, oh, well, you know, rich is 4.8. I do a t-test that this is equal to 12.5. negative 12.5, and I reject it. It doesn't work, right? Even though it looks like this thing is clearly not equal to negative 12.5, because I've got the coefficient here, I've got the standard error here, I can compose a t-statistic to test that this thing is equal to negative 12.5. But remember, poor isn't necessarily equal to negative 12.5. These are both random. And so depending on the correlation between them, imagine that the correlation is extremely negative, right? Well, if the correlation is extremely negative and they're both 0, I would get a positive estimate for one and I would get a negative estimate for the other, even though on average they're both 0. And so we could be tricked into thinking that they're not the same when they really are the same. The f-test isn't going to suffer from that problem, even though a t-test would. So don't do a t-test here. P-value? What p-value? Right? So this is clearly an f-test question. Let's go grab that formula. I want to make sure I have the right thing here. I'm going to select this. I'm going to take it with me. There it is. All right. So what do I need to do? I need the sum of squared residuals from the restricted model. I need the sum of squared residuals from the unrestricted model. And then I need degrees of freedom. This is the regression output from the model where I forced rich and poor to have the same coefficient. So what I've got here is a sum of squared residuals from a restricted model. Okay. Let's go back and see. Oh, wait. Degrees of freedom, right there. Degrees of freedom in the restricted model. Remember, degrees of freedom is the number of observations minus the number of coefficients in the model. So let's plug that right there. Okay. Now up here I've got my unrestricted model. Notice I've got the sum of squared residuals for the unrestricted model right here, and then degrees of freedom 87862. So I'm going to scroll down, sum of squared residuals, unrestricted model, very, very large number, right? 11 million here, 14 million here, 87862, 87862. Sum of squared residuals for the unrestricted model again is going to be 11 million, and we're going to have 87862 degrees of freedom. 87862. You're welcome to crunch this out yourself and verify what you get, but I do want to point to degrees of freedom, residual sum of squares, 87,000 observations. The residuals are something like 12 on average, so okay, sure, makes sense. Huge, huge sum of squared residuals. I'm going to go ahead and tell you what this comes out to. If you crunch this out, it's in the solutions, you'll see 12,276. That is not a small number, that is a big number. So what I need to find out is whether it's big enough to reject the null hypothesis, or whether I need to go and rethink things. Conclusion and reason. Well, where could I find out whether this is big enough to reject the null hypothesis? Somewhere in here there must be a table, right? I need critical values. Sure enough, go all the way to the end. Here it is. F distribution, critical values, 5% significance. You'll remember the F distribution has two different degrees of freedom. The numerator degrees of freedom is the number of restrictions. The denominator degrees of freedom is the actual usual degrees of freedom. So what we've got to figure out is how many restrictions there are, and then how many observations there are minus the number of coefficients we estimated in the unrestricted model. There is a caveat here, a little qualifier, which is on the exam, this regression output is not the regression output from that model, right? It was just put here as a placeholder. And so what we actually have in this regression output is 87864 degrees of freedom. There are two restrictions here. And so you'll notice this top degrees of freedom is 87864 minus 87862. This is going to give you 2 up here. which would mean the numerator degrees of freedom is 2. We actually only had one restriction in the model. So you could do this either way. You could put a 1 there. If you do, 12276 is going to double, right? Either way, you'll get the right answer because somebody gave you funny numbers up here. That's fine. This is the degrees of freedom from the unrestricted model. So 87867 observations in the data, subtract how many coefficients were in the model, and you get those degrees of freedom. Which again, you could look at that and you could say, wait a second, there were 87867 observations. I have 1, 2, 3, 4 coefficients in the model. So again, that's actually off by 1. It won't affect the outcome of the problem. But I'm just giving away the secrets for where these numbers actually came from. So what do? I have one restriction here, or two if you took this number as being serious. And then I have 87,000 effective observations. Go back to the F-test. I only have an F-test for 95% confidence, so I'm just going to have to make do with that. Numerator degrees of freedom, either 1 or 2, depending on which way you went with that little conundrum. Denominator degrees of freedom, well, 87,000 is not a small number. It is a bigger number than this. So I'm going to notice that my critical value is either 3 or 3.8. I'll go with the 3.8 just to be conservative. Let's have a look at that estimate one more time. And F-crit is 3.8. It's not even close, right? So if our estimated coefficient, or estimated F-stat is 12,000 and the critical value is 3.8, the conclusion is going to be reject, and the reason is going to be test stat than 3.8. Awesome. Calculate the marginal effect of an additional year of education for a rich person who has completed 16 years of school. Show your work. Okay. Marginal effect of education. Remember, we've got education and education squared in this model. So I need to take the derivative of hours worked. Show your work. So let's see. Derivative hours with respect to education is going to be derivative of beta 0, right? Remember the model. We've got beta 0, beta 1 education, beta 2 education squared. This is not there anymore. We'll have beta 3 and beta 4 poor, right? So derivative of beta 0 is going to be 0. Derivative of beta 1 education is going to be beta 1. And then we will have plus, I hate you, Microsoft. So we'll have beta 1 plus 2 beta 2 education, right? Not education squared anymore. Check this yourself, but I think you've done this derivative of a quadratic model a couple of different times, so you know what's going to happen. Beta 1 in this case was something like negative 0.31. Beta 2 is 0.01. And education is, let's see, I've got negative 0.3 and 2 is 0.01. Education is, as it says here, 16. All right, so 16 for that guy. I hate you, Microsoft. Crunch these out yourself. See what you come up with. You should get something that's about 3. Let's make that look more like a 3. 3.5. Right, so this is saying if you're at a college degree already, 1 more year of education, on average, I would predict you to work about another 3 hours per week. So check that and see if that's what you get, and then we'll pick up problem 2 in another video.